everyone. We've now come to chapter 4 here in our lecture on computational finance. We are talking about asset models. Asset models being a very generic term, heading for this chapter. We are in fact talking about stochastic processes and stochastic processes that are used to model asset price evolutions, asset price movements, and this is what we understand with asset models. And as you can see from the subheadings here and the subchapters, we'll start with a short discussion on the Wiener process and the closely related geometric Brownian motion. We'll then turn to the Black-Scholes-Merton model. I'll explain to you why it's not just the Black-Scholes model, but the Black-Scholes-Merton model. Usually one only says Black-Scholes. And later on we'll talk about jump processes, and we'll start with the jump processes and continue that next week. So you can see here that this is also covered in the investment and risk management textbook by Albrecht and Maurer in a slightly different fashion and using a slightly different notation. I hope the notation chosen for these slides is a little bit more self-explanatory than the one in this textbook, but I hope I will be able to explain this to you even if you are studying business or economics and not just mathematics and financial mathematics. Why is this so important to me? Because this is something I never really quite understood during my own studies. I hope not because I was too stupid, but I would assume that all the textbooks and all the lectures I read were simply not able to explain this to me without having a proper mathematical background at that time. Asset models and stochastic processes are something that you deal with in your mathematics studies and sometimes even in your graduate studies, not in your undergrad studies. But this is one area in finance that is actually quite simple if you know the right tools and if it's explained to you in more detail, but something that seems to be very difficult and complicated if you are not given the proper context. So we are trying to describe the time evolution of asset prices. This is a positive approach to asset pricing. Before, we've seen a normative approach, same in German, normativer, positiver Forschungsansatz. We are not trying to explain the basic fundamentals of asset prices. We are not trying to explain the dynamics, how risk factors interact and cause asset prices, but we are simply trying to come up with a suitable stochastic or statistical model that is able to describe empirical asset prices. We are taking asset prices as a given, and we are simply trying to find a model that best fits the data. This is a totally different approach than before in the factor models, where we were trying to explain the market microstructure of asset pricing, and here we are simply trying to find a good fit and a model that fits the data well. Okay. Now, which models are we looking at? We are looking at models in continuous time, Modelle in stetiger Zeit, meaning that changes can take place in continuous time and not just in discrete time. It's a little bit tricky. There are some advantages to looking at stochastic processes in continuous time, or even though usually you would think that asset prices can only be recorded and can only be observed in discrete time, today, tomorrow, in 2 days, and so on. Yet, if you think about the market microstructure of the security market, you would see that prices can be observed actually at any point in time. You're not really observing a price, but if you think about a security market and a stock market, you can only observe transactions that have taken place. And if you go down to high-frequency data, you can observe these prices at 5-minute intervals, at 1-minute intervals, at 10-second intervals. And you get the idea why it makes sense to look at asset pricing in continuous time in contrast to discrete time. Because discretization is just a simplification of a process that in its very nature is continuous in time. So we are using time-continuous stochastic processes. For everyone who is not aware of the definition of a stochastic process, stochastischer Prozess, if you take a random variable x, you're describing a phenomenon in nature that is stochastic. If you have a number of random variables, a number of phenomena you are observing, then you have a set of random variables, and I could be an element of an index set, capital I. So you have a set of random variables. And this is already a stochastic process. It's just a set of indexed random variables. Also eine Menge, Set ist Menge auf Deutsch, eine Menge indizierter Zufallsvariablen. It makes sense, of course, to use an index set that mimics periods or points in time. So if you take, left out the tilde here, if you take a set of random variables with a time index, that's a stochastic process. Why are we looking at a set of random variables? If you want to describe the number of people walking down the street within an hour, this is a random variable. The random variable has one unique distribution. But it could be that this phenomenon changes from now to next hour to the time in 2 hours and so on. So actually you are looking at a phenomenon that changes, meaning you might have different phenomena. And you need different random variables to describe this changing stochastic behavior. And here you have a set of random variables. The set of random variables is indexed by a set for a time index. And it could be that xi is equal to xi plus 1 and so on. Then it would simply be a set with one random variable. But this is only a special case of a stochastic process. Yeah? This is just a special case. So the general case is we have a number, maybe an infinite number of random variables. They might have the same distribution, but the distributions can also be different. And one important model for the time evolution of stock returns is the so-called Wiener process. Same word in German, Wiener Prozess. We also have the geometric Brownian motion. It can be derived from the Wiener process. I'll talk about that in more detail later on. And these are the building blocks of the Black-Scholes-Merton model for option pricing. And the Black-Scholes-Merton model won a Nobel Prize a couple of decades ago. And it's the most, I would assume, one of the most famous models we have in all of finance. And we'll later derive this model in detail for option pricing, and then we'll look at jump processes. So let's start with the Wiener process and geometric Brownian motion and geometric Brownian motion. Again, we are not looking for a causal model of stock pricing and asset pricing. We are not explaining the economics, how these stock prices have come about, but we are trying to find just a statistical model that fits the data best. And for some reason, people found out that actually a Wiener process and a geometric Brownian motion make sense, and they are able to describe stock return movements quite well in nature. Okay. And we'll start with random walk. What is a random walk? A random walk is a stochastic process in one or more dimensions. And the idea is you have a starting point. If, for example, we are now in 2 dimensions, let's assume we are walking on a plane, wir sind also in der zweidimensionalen Ebene. You start at this point, you choose a random direction, and then you take a random step into this direction of random length. So I could be walking into your direction and make such a step, and then I'll choose this, randomly choose this direction, I'll make such a step. Again, random direction, random step length. And that's, if you connect all these steps, that's a random walk. As you can imagine, and you will probably see why it's also called a drunkard's walk. Also der Weg eines Betrunkenen. It's a very random process. Random direction, random step length. And this is a random walk in 2 dimensions. A random walk in 1 dimension would simply be something can go up and can go down. Oh. Very simple. Only the step length is random. And at this point you might think, okay, this could be a suitable model for a stock price. Can go up, can go down, next period. But we don't know by how far it will go up or by how far it will go down. That's a random walk. What is interesting is that we are sometimes interested in the end-to-end length and the distance. For example, you will start here, take a walk to this point, then here, again, to this point, and so on. And what is now interesting is this is the starting point, this is the end point, and what is the distance between these 2 points, the end point and the starting point. Now, as you might imagine, if you always take a random direction and a random step length, the expectation of the end-to-end distance is 0. All these random walks will cancel each other out in the end because it's completely random. Furthermore, we have the expectation of the squared end-to-end vector, r squared, is proportional to n. So if you square all these distances and you take the average or the expectation, it will be proportional to the number of steps you've taken, and n is the number of steps. We'll need that later on. So that's a random walk. Now, if you want to compute the variance, you will see, take the expectation of r minus the expectation of r squared. So the variance is again proportional to the number of steps. And this is interesting only for one reason at this point. You might have seen in some textbooks some transformation rules and some conversion formulas to convert a 1-day var into a 10-day var, value at risk. And what you do is you take the square root of t. And the only reason why you are doing this is because implicitly all these models assume some kind of a random walk or a Wiener process, and you are scaling it. If you're changing it from 1-day to 10-day var, you're scaling it by t, and then you need to make this adjustment with the standard deviation, and actually then you have to take the square root of n, and in this case that's t. Okay. Now, what else do we know about the end-to-end vector of a random walk? The end-to-end vector of a random walk is normally distributed with expected value 0, expectation 0, and variance b squared times n, where b squared is, as you can see, the sum of these expected squared step length of the single steps. So, for example, this is R1, and this is R2, R3, R4, and so on. And for some reason, we don't need to know why here, but if you assume a random walk for your prices or stock returns, suddenly you are led to the normal distribution. And I'll talk about this in a second. But as you can see here, a random walk assumption for the stock price means that you have an implicit assumption of a normal distribution for your stock prices, or for the associated end-to-end vector. And this is quite important to me, at least, because in many textbooks you will see statements, in German textbooks on management and business, you will see statements like, we are assuming a normal distribution for stock prices or stock returns. And in most cases this assumption is not justified. There's no explanation given why you should use a normal distribution. Well, in fact, you have to go one step back. In most of these models, if you take the original research papers, you will not see a normal distribution assumption, but you will see the assumption of a random walk, or more precisely of a Wiener process or a geometric Brownian motion. And this assumption implies that the resulting stock prices or stock returns are log normally or normally distributed. So you are not assuming a normal distribution, but you are assuming a different thing, and this different thing is a random walk or a geometric Brownian motion, and as a result you get the normal distribution. But the modeling assumption is completely different. But most, unfortunately, especially older textbooks on risk management, in German at least, they don't get that. If you are not familiar with stochastic processes, and with some stochastics at least, you're done when you hear the word normal distribution. Then that's even way too much mathematics for you. Okay, so we're trying to use a random walk. What are we doing? We're still trying to find a model for the time evolution of stock prices. So one could think about using a random walk in one dimension. Stock price can go up, can go down. Okay, let's try that. We have a change in time. Time goes on and time elapses per step of the random walk, and the time that elapses is dt. D already indicating a difference. This is a delta. The delta in time, dt. During this whole random walk, from small t to capital T, we have n steps. So each step has the length in time dt. So n times dt should equal the time that elapses from t to capital T, and that's obviously capital T minus t. This is what we have here. N steps, time length dt. The random walk is now used to model the changes in the stock price. The stock price is st, changes up to s capital T, and in each time period dt we have a change dsi from point si minus 1 to si. Could have also written t here, actually the same. So we have a change in the stock price. That's dst. Now, if the price were a random walk itself, if the stock price could go up and go down, we would get the following problem. The individual steps, dsi, would also be random walks, because I left this out. If you start here and you have a random walk that looks like this, the random walk has a property that is called self-similarity, Selbstähnlichkeit, meaning that if you cut out one of these steps, let's take this one here, this step is also the end-to-end vector of a smaller random walk. In other words, the random walk perpetuates itself. If you take out one little step, it's again a random walk. However, a security, a stock with a price of, say, 1,000 euros would then have the same price fluctuations as a security with a price of 10 euros. And that's unrealistic. Therefore, we shouldn't use a random walk for the prices, but for relative prices, aka returns. Now, if we were to use the discrete changes, die diskreten Renditen, SI divided by SI minus 1, it turns out that by adding all these changes, we don't get the end-to-end vector, because you need the following. If this is S0 here, and it changes to S1, it goes on to S2, and so on, and then S3, S4, the following needs to be true. The difference S4 and S0 has to be equal to S0 plus S1 plus S2 plus S3 plus S4. The end-to-end vector has to be the same as the sum of all those individual steps. Simple linear algebra or vector space algebra. If you think about it geometrically, it makes sense. Should be the same if you go from S0 directly to S4, then simply going from S0 to S1, S2, S3, and S4. This needs to be the case. But the direct connection from S0 to ST cannot be represented by a sum of those individual changes, discrete changes. You cannot, let me just write this out for you, ST would have to be the same as S1 through S0 plus S2 through S1 and this is not the case. So discrete changes modeled by random walk doesn't work. But if we take the log returns, if we take the logarithm, the natural logarithm of our prices, that is ln Si, and if we take the difference understood as the difference here between log or ln Si and ln Si minus 1, this works. And actually this is why in many models we are using log returns instead of discrete returns. First of all, if we are using continuous model or models in continuous time, why would we use discrete returns? It makes more sense to use discrete continuous returns with continuous models. But if we are taking log returns, then it's quite simple to see that the natural logarithm of st S0 can be written as the logarithm of st minus the logarithm of S0. So this works here. If you simply add up all those changes and all those steps, you get the end-to-end vector of the random walk. Okay. Yeah. Well, I've written this down here. So as a first result, you can see that you can use a random walk, but you cannot simply apply it to the prices or discrete returns, but you can use it on the continuous log returns. Then it makes sense. Okay. So that's a random walk. Now let's turn to a Wiener process. What's a Wiener process? A Wiener process is probably the most basic and simplest form of a stochastic process. A Wiener process is a continuous stochastic process that has normally distributed independent increments. What is an increment? German Zuwächse. Well, if you have a set of random variables indexed by t, you are interested in the changes, in the increments, in den Zuwächsen. And those increments are just regular differences between this random variable and the next one, and so on. So what does this mean? A Wiener process is a process that has normally distributed independent increments. So these differences between t and t minus 1, t minus 1 and t minus 2, and so on, all these differences, all these changes are independent. Doesn't make any difference whether you are at t, t plus 5, t plus 20. Those changes are always independent of each other. They don't change each other, and they follow a normal distribution. And if a Wiener process changes dt, if time changes dt, we'll have a change in the Wiener process of dw, and these changes are normally distributed. And you usually write this in the following way. You say the changes of the Wiener process, they are given by a standard normal distribution times the square root of dt. This is a Wiener process, one way to write a Wiener process. And as you can see, the distributional law doesn't change over time. dt, the change in time, is always deterministic. You know that tomorrow at the same time, one day will have elapsed. So time, even though we don't know what happens tomorrow, we know that tomorrow will be one day ahead of today. So dt, the changes in time, are always deterministic. They are not stochastic. So we are taking the time period, dt, take the square root, but in the end, the changes are a scaled standard normal distribution. And that's a Wiener process. A very basic model, a very basic example of a stochastic process. And yeah, you only need to get a little bit familiar with this way of writing things, that these are the changes of the process. These are not the variables that make up the process, but these are the changes, the increments. A slightly different definition here, and you can see, maybe you can see this a little bit better. The stochastic process, xt, is called a Wiener process or Brownian motion if the following holds: increments xt1 minus xt0 are stochastically independent. The distribution of the increments only depends on the leg h and not on the position, and they are normally distributed. And you can see here xt minus xs is normally distributed with mu of t minus s and sigma squared of t minus s. These are called the drift and the diffusion. Now let's go through a couple of things here. First of all, as you can see here, the distribution can be different. It's not always just a standard normal distribution, but it is a normal distribution, and the type of normal distribution depends on how far you are looking into the future. That's the lag. If you're looking 5 days or 20 days into the future, assuming now, falsely assuming that this were a discrete process. Obviously, we are still in continuous time, and we are talking about infinitesimally small changes in time. That's the first thing. Second thing is that we are writing mu and sigma squared as functions of t minus s, this lag here, and mu and sigma squared always were what? The expectation and variance of a standard normal distribution. And in our discussion of portfolio theory, we also described the expectation and sigma squared, the variance with this notation. However, you cannot talk about expectations and variances anymore. Why? You have a process, and a process is an infinite set of random variables. And the expectation and variance operators are defined for random variables. And these parameters, they change a little bit. However, the expectations and variances are driven by these two functions, and they are determined by these functions. So mu and sigma squared are driving the expectations and variances of all these individual random variables, but to be mathematically correct, you cannot call them expectation and variance, so instead you're calling them drift and diffusion, to signal that, yes, they are in fact driving the expectation, the average level, and they are driving the variance, but they are not exactly variance and expectation. I'll repeat this in German. Mu und Sigma sind üblicherweise Erwartungswert und Varianz. Aber Erwartungswert und Varianz sind zwei Momente einer Verteilung. Hier haben wir aber unendlich viele Verteilungen. Und wir können in einem solchen Prozess jetzt nicht alle, die Erwartungswerte und Varianzen unterscheiden sich von xt zu xt plus 1, weil das Funktionen letztlich sind in dem Lag. Aber natürlich am Ende sind alle Erwartungswerte und Varianzen getrieben von diesen beiden Funktionen μ und Sigma Quadrat. Jeweils Erwartungswert und Varianz. Und deswegen nennt man das dann nicht mehr Erwartungswert und Varianz, weil das formal nicht richtig wäre. Es ist ja nicht die Varianz. Was ist überhaupt die Varianz? Es gibt ja unendlich viele. Sondern das sind dann Drift und Diffusion. Drift beeinflusst natürlich maßgeblich die Erwartungswerte. Diffusion, wie man das schon erwarten kann, die Varianzen. Deswegen ist das also hier ein bisschen anders benannt. We can also write the Wiener process as xt equals W0, a starting point, plus mu t plus sigma times the square root of t times a random variable zt, that is a standard normal distribution. So this is a different way of writing a stochastic process, a Wiener process. By the way, why are we writing this later on in this way? You might have seen this somewhere. Has anyone of you seen this before? This way of writing a stochastic process? Ich habe schon die Differentialschreibweise. No, okay, I'll get back to this later. But as you can see here, a Wiener process can be defined by defining the xt's themselves. Now we have the covariance between xs and xt is the minimum of s and t times sigma squared, the diffusion. And we obviously have the expectation of xt is W0, the starting point, plus mu t. And the standard deviation of the process, or more or less of the variable xt, is sigma, the diffusion, times delta square root of t. Okay. And if we are interested in a standard Wiener process, the standard Wiener process is given by starts at 0, has expectation 0, or drift 0, diffusion 1, meaning that in the end xt is given by square root of t times a standard normal distribution. This is the same we've seen here. Actually, this is more or less a standard Wiener process. By the way, what does this mean? It means a standard Wiener process is nothing but a normal distribution. A set of random variables that has normally distributed increments, and those increments might change a little bit and the parameters might change a little bit depending on the lag you're looking into the future. But again, this is a normal distribution, but it's a standard Wiener process. Okay. Now, how does this look like? It's very simple to simulate a path from a stochastic process, meaning that we are taking one event, and we are fixing this event and looking at the values of all the different random variables xt. remember that, in fact, a stochastic process is more or less always given in 2 dimensions. I can give you a very simple example. I can form, let's take a dice. A die, no. Yeah, die. Singular. Würfel. A die takes the values 1, 2, 3, 4, 5, 6. And if I now construct a stochastic process by throwing this die, what would I get? Results. Oh. And then t. T equals to 1, t equals 2, t equals 3, and so on. You have potential outcomes. A random variable, if I have one die, it has 6 potential outcomes. And if I throw it 1,000 times, in every one of these instances, I can have one of those 6 outcomes. And a stochastic process is thus more or less always given in 2 dimensions. The possible outcomes can, if it's a continuous random variable, you have infinite outcomes, and the set of time periods. Nochmal kurz auf Deutsch. Ein stochastischer Prozess hat offensichtlich 2 Dimensionen. Sie können ein Ereignis, wir reden ja immer noch über Zufallsvariablen. Und Zufallsvariablen sind ja was? Das sind Variablen, die mehr oder weniger allen Ereignissen eine Wahrscheinlichkeit zuordnen. Beim Würfel diskret 1, 2, 3, 4, 5, 6. Und wenn ich jetzt einfach einen Würfel einmal wähle, habe ich 6 mögliche Ereignisse und ich habe den einmal geworfen. Wenn ich ihn jetzt 1000-mal werfe, habe ich ja in jedem Zeitpunkt immer wieder die Möglichkeit, dass ich eine 1 oder eine 2 oder eine 6 würfel. Deswegen habe ich also eigentlich hier so eine Matrix, die möglichen Ereignisse hier im diskreten Fall endlich, ansonsten überabzählbar unendlich viele, und ich habe hier meine Zeitpunkte. Und das, was ich dann als Pfad eines stochastischen Prozesses bezeichne, ist mehr der Querschnitt, wenn ich dann nämlich sage, ich gucke mir mal an, was letztlich rauskommt, wenn ich dann so durch einen Prozess gehe, wenn ich den also durchschaue. Weil ansonsten müsste ich ja sagen, ich müsste in jedem Zeitpunkt alles irgendwie betrachten. Das ist also hier Pfad. Path of a Wiener process. And I can very simply simulate a path from a Wiener process. I start in the first line by taking rand n, state 100. What is rand n in MATLAB? Rand stands for random number generator, and n for normal distribution. Wiener process is more or less connected to the normal distribution, so we are simulating 100 random numbers from the normal distribution. T equals 1, n, we have 500 steps. dt, the change in time, is now 1 over 500, ein 500stel. dw is a vector of zeros. We start by initializing the vector dw by zeros, or with zeros. W as well. And now what? dw, the first slot, we need a starting value. Square root of dt times rand n. Okay. W1 is just dw1. We need to initialize the process, and then we have a for loop. For all the remaining steps, 2, 3, 4, 5, up to 500, we do what? The change, the increment is given by a Wiener process. It's the change in the process. dw is given by square root of dt times z. So we simulate from z, that's rand n, times square root of delta dt. And then we have the change in the process, and what is the next state of the process, also der nächste Zustand. Obviously, previous state plus the change. We start here at w0. We need dw1 question mark, and if we then take dw plus dw1, we get w1. Then we need dw2 if we edit, might move here and so on, and plot. This is how it looks like. We start here at 0. That's our starting point, right? Somewhere near 0. And then we simulate normally distributed independent increments. We add those increments to the last state of the process. And then we move on and move on and move on when we have 500 states here. That's one path of a Wiener process. If I had left out the axis, and if I had told you this is a stock price, there's at least a 50-50 chance you would have believed me. It definitely looks like a stock price. Okay. Now, next we consider an infinitesimally small change in time, dt. As always, we're in the framework of continuous time. And for the logarithmic prices, d, ln st, we get, under the assumption of a random walk, that the changes in the logarithmic prices are given by sigma times a standard Wiener process. And you see here the diffusion, sigma, comes out of the variance of the logarithmic stock returns, or the log returns. So at this point, you already know that what do we do in finance if we are modeling stock prices? We are taking log returns, continuous modeling. We assume a random walk. We assume the log returns follow a random walk in time. And if we assume a random walk, we get this Wiener process for the time evolution of stock price returns. We don't assume a normal distribution. We assume a random walk and thus a Wiener process and stock returns, log returns to follow a Wiener process, and we get the normal distribution as a result. But we don't assume it. This model, however, is not yet flexible enough to model real-life stock returns. As you can see from this path, it starts at one point, but more or less, if we were to continue it even longer, it will just wiggle a little bit around 0, around the starting point. Why? Because we are just like the random walk. You take a step left, you take a step right, and in the end, if you only take enough steps, all those random steps with random direction will cancel each other out and you will stay put. Not a very good model for a stock price. There should be some kind of a drift, that stock prices go a little bit up, they go a little bit down, and they have some variance. So we need to mix in a drift. And this is done here. We take the Wiener process and we include mu dt. This is a deterministic. Actually, independent is not fully correct. Obviously, it's independent, but it's also deterministic. dt and mu, they are deterministic. It doesn't change the distribution away from a normal distribution. It only changes, obviously, the expectation. Ändert die Verteilung nur in Erwartungswert. Meaning that we just take it to the next level and could be like this and could also be a little bit different. Now this is something you might have seen if you had ever have a look at a textbook on risk management and option pricing derivatives. You see, for example, something like this. The returns are modeled as mu dt plus sigma dwt. This is the differential notation of a stochastic process. Stochastic processes are a part of what is called stochastic calculus or stochastic analysis, stochastische Analysis. Why is it called stochastic calculus? Well, these models can be expressed as differential equations, and thus they can be integrated and differentiated. And you take, for example, this definition here, and because you're interested in the changes, you need to differentiate this. Same you would do with any regular function. And if you take the differential, you get this different notation, and it can be interchanged to an integral notation or a differential notation. And this is why in many textbooks you see this differential notation, but you should remember that it should be interpreted as an infinitesimally small change in RT is given by a parameter mu times the infinitesimally small change in time plus the changes of a Wiener process. I'll say this in German again, because I think this is important. In deutschen Lehrbüchern finden Sie oftmals also vor allem in den schrecklichen BWL-Lehrbüchern, finden Sie oftmals einfach so diese Schreibweise hingeknallt. Stochastische Prozesse sind letztlich darstellbar. Der Kollege, der Kommilitone hier vorne als Mathematiker wird mich hoffentlich korrigieren, falls ich Quatsch erzähle. Stochastische Prozesse sind letztlich darstellbar auch als Differentialgleichung. Und dementsprechend kann ich sie, am Ende sind es Integrale. Und ich kann dann, erinnern Sie sich mal an die Analysis, Integration und Differenziation, also Ableitung ziehen, sind zwei Seiten ein und derselben Medaille. Wenn Sie die Funktion nehmen und ableiten, können Sie auch über das Integrieren wieder über die Stammfunktion zurückspringen bis auf eine Konstante. Das ist der Zentralsatz, Hauptsatz der Analysis. Und was Ähnliches haben Sie hier auch. Dadurch, dass das Differentialgleichungen sind, wie löst man Differentialgleichungen? Indem man sie integriert. Ja, das Lösen von Differentialgleichungen nennt man auch Integrieren. Und dementsprechend ja, können Sie hin und her springen. Und eine Möglichkeit ist eben, dass Sie hier sehr schön zeigen, also die eigentlichen Zufallsvariablen xt sind so gegeben. Eine andere äquivalente Schreibweise geht über die Differentialschreibweise, dass Sie nämlich sagen, Sie schreiben nicht xt, sondern Sie schreiben das Ganze hier mit dt. Erinnern Sie sich mal an Ihre Mathematikausbildung an das totale Differential. Kennen Sie vielleicht auch noch, dass Sie haben eine Funktion und Sie sind interessiert an dem totalen Differential der Funktion. Ja, dann arbeiten Sie auch mit den Ableitungen und dann steht da irgendwie sowas, df ist gleich irgendwie Ableitung mal dx plus bla bla bla, Ableitung mal dy. Ja, also das habe selbst ich in einem BWL-Studium noch gelernt, das totale Differential. Gut. Und hier ist es letztlich genau das Gleiche. Und Sie müssen es einfach so immer interpretieren, die Veränderung in dem Prozess, der Sie interessiert, also jetzt hier ST oder DLNST, ist gegeben, diese Veränderung, durch die Veränderung hier in der Zeit, die ist immer deterministisch, mal ein Parameter, der ist gegeben, plus Diffusionsparameter Sigma mal diese Veränderung in dem Standard-Wiener-Prozess. Und die Veränderung in dem Standard-Wiener-Prozess ist nichts anderes als einfach weißes Rauschen mit der Normalverteilung, was dazu gewürfelt wird. Gut. Ich sage das deswegen, weil es gibt zwei Arten von Lehrbüchern. Entweder welche von Mathematikern, die fangen sofort auch mit Wahrscheinlichkeitsraum und mit Hardcore-stochastischer Analysis auf der ersten Seite an, da versteht man kein Wort, als Normalsterblicher, ohne Vorkenntnisse. Oder aber es gibt BWL-Handbücher und Lehrbücher, die schmeißen dann einfach diese Differentialschreibweise auf die erste Seite und können selber nicht erklären, was da eigentlich gemacht wird. Und dann versteht man das ganze Prinzip nicht. Auf die Integrale und in die Integration will ich hier gar nicht eingehen, das wäre auch zu viel. Okay. This is our next type of model. In essence, the log returns. Remember, this is the difference in the logarithmic prices. In other words, log return. Log return is given by mu dt plus sigma dwt. Standard Wiener process times a diffusion parameter plus a deterministic and independent drift. Could simply be 5 constant for some reason. You can also include non-constant drifts and non-constant volatilities. It would simply mean that instead of mu constant, you would substitute mu constant by a function in, say, st and t, and you would use sigma also as a function in st and t. It makes the model more realistic, makes it more complicated, but it's still a Wiener process. On a side note, the prices st are log normally distributed, the returns are normally distributed. So I always get confused by the two things, because in textbooks and articles you will read prices are normally distributed, returns are normally distributed, and something. No, the returns are normally distributed, and if you assume such a model, the prices will be log normally distributed, log normal verteilt. Okay. Random walk, Brownian motion, Wiener process. Actually, 3 words for the same thing. A Wiener process is the mathematical model. Brownian motion is the natural phenomenon that is modeled in mathematical physics by using a Wiener process. Brownian motion is the phenomenon of minute particles diffusing in a fluid. Also Kleinstpartikel und die Diffusion von Kleinstpartikeln in einer Flüssigkeit. Wenn Sie also einen Eimer mit Staub nehmen oder Sandpartikeln und Sie schmeißen den in einen Eimer mit Wasser, dann ist die Verteilung, die Art und Weise, wie dieser Stoff, der Festkörperstoff, wie der in der Flüssigkeit diffundiert, dieses Phänomen in der Physik ist die Brownsche Bewegung. That's Brownian motion. That's the phenomenon in nature that is described by a Wiener process. And a Wiener process is the scaling limit of a random walk in dimension 1. This means that if you take a random walk with very small steps, you get an approximation to a Wiener process and less accurately to Brownian motion. So, in some cases you will see Brownian motion, some cases you will see a random walk assumption, Annahme eines random walks, or you will see a Wiener process, basically all the same. Brownian motion is the phenomenon, Wiener process is the model, and random walk is a special case. Now, we have assumed a stochastic process in the following form. dst equals ast dt plus bst dw. It only means that we have a drift function A and a diffusion function B, both depend on t and s, and we are now modeling the stock price. dw is the standard Wiener process, and in fact this is the general diffusion process, der allgemeine Diffusionsprozess. It's a little bit more general than the one we've seen before, but it's quite simple to see. You can, for example, also use this here, and you can subtract this out here and get it to the other side, take the logarithm, and then you get the stock returns again. Now, what is a geometric Brownian motion? Geometrische Brownsche Bewegung. Geometric Brownian motion is again a stochastic process, st, and we say that st, the process st, follows a GBB, a geometric Brownian motion, if the following holds. St is given by st0 times the exponential function, and this, wt is again a Wiener process, or a little bit nicer, the differential notation dst equals mu st dt plus sigma st dwt. That's a geometric Brownian motion. M, if we set m equals to mu minus sigma squared divided by 2, this implies that if we set this here, you see that the log returns are again given by m dt plus sigma dwt. And m is the current continuous time mean return, and mu is the current mean discrete return. So that's a geometric Brownian motion. The difference is only that instead of mu dt and sigma dwt, you squeeze in st, the process itself. And what does that mean? First, st is usually assumed to follow a geometric Brownian motion. Stock price, geometric Brownian motion. That means, it implies that the changes in the stock prices follow this process. That means the log returns follow a Brownian motion or a Wiener process. And as a result, we get the assumption of a geometric Brownian motion for the stock prices. Log normally distributed prices and normally distributed log returns, moving from a geometric Brownian motion to a random walk for the log returns. And that's the formal and correct way of stating the assumption and differentiating between the assumption and all the results from that assumption. Ich bin da sehr penibel und sehr pingelig, aber ich glaube, das ist wichtig, weil Sie lesen das überall falsch. Sie unterstellen nie eine Normalverteilung. Sie unterstellen eine geometrische Brownsche Bewegung für die Aktienkurse, für die Preise. Daraus resultiert äquivalent die Annahme einer Brownschen Bewegung oder eines Random Walks oder eines Wiener Prozesses, was alles letztlich das gleiche ist, für die Log Returns, für die stetigen Log-Renditen. Und damit haben Sie log-normal verteilte Preise und normal verteilte Log-Returns. Und an der Stelle setzen die meisten BWL-Lehrbücher bei uns immer ein und sagen, wir unterstellen eine Normalverteilung für die Renditen. Das ist falsch. Sie unterstellen nicht einfach eine Normalverteilung für die Renditen, sondern Sie haben da schon ein viel ausgefeilteres und ausgeklügelteres Modell für die Preise und etwas, was man in der Physik, in der mathematischen Physik eben kennt. Okay. Now, why are we using this at all? Why are we needing it? We'll now move from the geometric Brownian motion to the Black-Scholes model. An important question now is, which stochastic process a function f in S and t follows if the change in S, t is given by a geometric Brownian motion or Brownian motion, and we are interested in a change df. We are looking at a function in the price S. Okay. Next we need Ito's lemma. Berühmte Lemma von Ito. We're doing, first of all, we have a function f, and it's a function in st and t. We're not looking at the subindex here, but again, st obviously is stochastic. T is deterministic. Function in S and T. We are interested in a change of the function, df. First total differential, and we do a Taylor expansion. The change, you don't need to know why this is, you don't need to know how to compute this, but simply accept the fact that you do a Taylor series expansion, Taylor Reihenentwicklung, and the change in the function is then given by the partial derivative of f with respect to s times ds plus the partial derivative of f with respect to t times dt plus half of the second partial derivative of f with respect to s ds squared, and so on and so on and so on. Sorry if I'm switching to German all the time. Only Germans left here. Das ist eine ganz gewöhnliche Taylor-Reihenentwicklung. Sie kennen das mit dem Satz von Taylor aus der Analysis. Eine Funktion kann dargestellt werden exakt in einer Umgebung von einem Punkt mittels seiner Taylor-Reihe. Und die Taylor-Reihe ist was? Das ist eine unendliche Summe von Termen, die letztlich immer eine partielle Ableitung enthalten und dann höhere, oder also nicht nur partiell, geht auch eindimensional, aber dann immer höhere Ableitungen enthalten und entweder die Ableitungen verschwinden irgendwann, werden gleich 0, dann ist es okay, das ist eine endliche Reihe, oder es geht eben ein bisschen ins Unendliche fort, aber Sie können die Funktion ersetzen durch Ihre Taylor-Reihe. Das nennt sich Taylor-Reihenentwicklung. Entwicklung verstanden, dass Sie quasi irgendeine Funktion approximieren, ersetzen. Ja, Sie entwickeln die und ersetzen die durch was Einfaches. Okay, so this is a Taylor series expansion here in a rather complicated case, but still, the change in df is given by the right-hand side, and you can rearrange this a little bit. And you can see here, it's the first partial derivative with respect to the stock price. Let's call S by its name, that's the stock price. First derivative with respect to the stock price, a function a in st dt plus b function b of s and t, Wiener process, plus partial derivative with respect to time times dt plus half the second derivative with respect to the stock price again times la 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 plus the rest. And all the remaining terms have at least dt squared or dt to the third power or to the fourth power, so it's imprecisely spoken of the order of dt squared. And all the terms include dt squared, dt to the third power, and so on, higher powers of dt. Now, very simplistically, we have the expectation of a squared Wiener process is dt, and the variance of a squared Wiener process is proportional to dt squared. What does that mean? You can see here that you have dw squared here, and the idea is now the following. We are looking at a process in continuous time, meaning the change in time, dt, is infinitesimally small. And if you square something that is close to 0, what happens? It is even closer to 0. If you square 0.1, what happens? It becomes 0.01. If you square now 0.01, it becomes smaller and even smaller and even smaller. And dt already is so small that it's infinitesimally small. So by squaring it, it is almost 0. And this is the central idea in Ito's lemma, that if you are approximating this linearly, that you can simply take the whole equation and throw everything out that includes dt squared, dt to the third power or to the fourth power or again. So what happens? Gone. Where do we have it again? And now we have to look at dw squared. What happens with dw squared? The variance of dw squared, of a squared Wiener process, the variance is dt squared. We said that the central assumption here in linear approximation, that this is 0. If the variance is 0, this is no longer a random variable. It's deterministic. And if something is deterministic, it's equal to its expectation. Eine Zufallsvariable mit Varianz 0 ist keine Zufallsvariable mehr, die ist deterministisch. Und dann hat sie auch keinen Erwartungswert, dann ist sie der Erwartungswert. Dann ist das der einzige Wert, der vorkommen kann. Heißt, meaning, dw squared is set to dt. approximately. And this leads us to, we cross out dw squared, that's dt. We cross this out, and now we only need to simplify the remainder. And this leads us to Ito's lemma. Ito's lemma states, it's not 100% perfect, mathematically speaking, but it's sufficient for our purposes. For an infinitesimal change of the function f in a diffusion process S and time, with a small, infinitesimally small change dt in time, we get the change of the function is given by yada 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 dt plus yada 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 dw. So let's call this a star times dt plus b star dwt. And this is, again, a diffusion process. That's the main result of Ito's lemma. If you have a diffusion process, the change in any function in this diffusion process is again a diffusion process with different drift and different diffusion. And you can see here, if you rearrange this a little bit, you get this. This is A and this is B. No? Or A star and B star. That's Ito's lemma. If you work more in this area of finance, at some point you will memorize Ito's lemma, because it's so fundamental. But the interpretation is quite simple. If you have a diffusion process, S, and you have a function f that depends on S, the change in the function, in any function in S, is again a diffusion process. Different drift, different diffusion, but still the basic form is the same. It's a diffusion process, only with different parameters. And we'll need this later on. We can further reduce this to this here and this, and we can now derive the Black-Scholes pricing formula. Why? Now, I've always talked about a function in S, but as you might have guessed by now, it's just all about financial derivatives. We have a stock price S, T, and we have a price of a derivative, PT, and PT is obviously a function in ST and T. We are only interested in the derivative price. That's why we need a generic function f in ST and T. So, that's why we need this. We are looking for the value, the price of a derivative, on an underlying stock, ST, at time t. So, we have V as a function in S and T. We assume the stock price follows this probably geometric Brownian motion, but we can assume a general diffusion process, A S T dt plus B dw. We write this a little bit different. We are using an average yield and average volatility. So we have ds changes according to mu tilde S dt plus sigma S dw, geometric Brownian motion. And then what happens? We know from Ito's lemma, any function, the change in any function in S and T is given by this, a different diffusion process. This is the delta, the option price. Let's assume that's an option we are looking at. Could be any other derivative. The change in the option price is given by a diffusion process. And this is the drift. And this here is the diffusion. As you can see now, Ito's lemma does not drop from the sky. It's the fundamental ingredient in deriving the Black-Scholes model, because we are interested in a change in a function of the stock price, and that's the derivatives price. However, and this is so important to me, when I learned about option pricing in my studies, I was simply given the Black-Scholes formula. I had no idea how it was derived, how they came up with this model, and I was not able to see the beauty of the proof. The beauty here are actually two things. First of all, and this is why these people got a Nobel Prize for it, they were the very first to think about this idea: let's use some very well-known models from mathematical physics and simply model stock prices by using something we know from physics. First assumption. And back then, 30 years ago, or 40 years actually nowadays, 40 years ago, there weren't too many people from physics working on finance. So these guys, Black-Scholes, Merton, they were the first ones to came up with the idea to use models from physics to model stock price evolutions. The second thing is, not just assuming this model for the stock prices and log returns, but seeing that, in fact, you can use Ito's lemma in this case, and the result is that you can not only model stock prices, but you can come up with the price of a financial derivative that by definition is a function in the stock price and the point of time you're right at. And what is very important to me is, and I'll write this extra large on the slide, so far I've only talked about this, F. But what is F? It's a function in the stock price. It's a derivative in the stock price. I haven't talked about whether it's an option, whether it's a call, whether it's a put. Doesn't matter. The model, the Black-Scholes model in its very nature is general to the max. It's completely generic. It can be applied to any financial derivative. It is not just a model that gives you a result for a European plain vanilla call or a put. The model itself can be applied to any financial derivative, because the only assumption you make is it's the price of the derivative is a function in ST. Well, any derivative has a function, is a price that is a function in ST. And up to the very last point of the model, we will not specify what type of derivative we are looking at. It's just F, function in ST. And it can thus be used to price any derivative. Okay. Now, what do we do next? We take the derivative with a value v of s and t, and we build a portfolio. One option, let's use the option of one derivative, and a number delta of underlyings, could be stocks. So let's make the special example, special case example, one option and delta stocks. And as you can see, the portfolio is constructed by going long in the derivative and going short in the underlyings. We are buying the option, we are selling short the stocks. One option, delta stocks. Okay. The value of this portfolio is given by d pi is given by the change in the option price minus delta times the change in the stock price. Quite simple so far. Write this out. We know dst by our assumption of a geometric Brownian motion, and we know the change in the option price from Ito's lemma. So dv becomes this, and this is just delta ds. Rearrange it a little bit, and you can see we have something in dt and something in ds. Again, remember, dt is deterministic. This here then is also deterministic. So d pi, the change in the portfolio price and portfolio value, becomes deterministic if this part here is 0. The stock price is stochastic. The stock price can change. Time, well, we know how time changes. Tomorrow will be tomorrow, will be 1 day ahead, not 2 days. So the price of the portfolio becomes deterministic. What does deterministic mean in this sense? If the value of the portfolio becomes deterministic. Risk-free. If there is no change to the portfolio value, if it cannot change, well, then it's risk-free. This becomes risk-free if and only if what happens? If the second term vanishes, becomes 0. When does it become 0? If delta is set to this partial derivative of the option price with respect to the stock price. In this case, this becomes 0, this becomes 0, this vanishes, and the portfolio becomes risk-free. Ergo, if we set the number of underlyings delta equal to the partial derivative of the option price with respect to the stock price, this portfolio becomes risk-free. So far clear? And now what happens? This is what I just said. If we set delta to this partial derivative, this is called a delta hedge. You might remember, if you have taken my risk management class, the partial derivative of the option price, of the derivative price with respect to the stock price is called what? The option delta. That's the option delta. It's a Greek. The sensitivity of the option price to a change in the stock price, in the underlying price. And in this case, this is also a perfect hedge. We are able to perfectly hedge the risk of this portfolio. Risk vanishes. And now I do what? The next critical assumption, or it's not an assumption actually, but in an arbitrage-free market, this next step immediately follows. We have a portfolio of an option and delta underlyings. The number of underlyings specifically chosen with the option delta, meaning that if the option goes up, the delta underlyings go down in exactly the opposite direction, cancelling out each and all risk of this portfolio. And what should now be given in an arbitrage-free market? In a market where you cannot earn profit from an arbitrage strategy. Very simple. Actually, this is done in many of these models. In the end, if something is risk-free, what should be the case? Oh, come on. What return should this portfolio pay if the market's arbitrage-free? Not 0. The risk-free rate. Should pay the risk-free rate. In this case, it's simply R times the portfolio value times dt. And here you see the change of the portfolio if it's deterministic. And this should be the case on an arbitrage-free market. So you simply set this equal. And if you rearrange this a little bit, you get the Black-Scholes differential equation, die Black-Scholes Differentialgleichung. In fact, it's a stochastic partial differential equation. It's a differential equation, meaning it's an equation that includes derivatives, function derivatives, differential quotients. It's a partial differential equation because it includes partial derivatives, and it's stochastic because it includes random variables. Stochastische partielle Differentialgleichung. As you can see, it includes partial derivatives, and in the end, it's set to 0. It states, for arbitrage reasons, the return on a delta-hedged portfolio consisting of one derivative and delta underlines should give and should pay out the risk-free rate. That's all we have here. Now, have you ever seen have you ever seen differential equations? You probably have, right? Yeah. The rest of you, have you ever seen a differential equation? A differential equation, as the name suggests, is an equation that includes a derivative of the function. A very simple example of a differential equation would be something like this. For simplicity, we also sometimes write this like this. Actually, a better example is this. This would mean that f of x is the first derivative of f. That's the same. Yeah? Simply for simplicity, you instead of f of x, you write y. Y, first derivative is equal to y. Can you give me the solution to this differential equation? It's a differential equation. It includes derivatives, and it's an equation. What's the solution of this differential equation? No one? It's too late, I guess. At first, it's a trick question. There is not just one solution. What solution are we looking for? What could be a solution? And this is the first thing you need to know about differential equations. Even though it's an equation, the solution to a differential equation is not a real number, it's a function. You're looking for functions that fulfill this equation. And what function fulfills this equation? The function that is constant to 0. If you take 0 and you take the first derivative, it's 0. That's one solution. Can you give me a second solution? Yeah. The exponential function. Yeah. The exponential function, if you take the derivative, it again is the exponential function. So you already have two solutions. And you can see, with this very simple example, you can see some basics about differential equations. First of all, solutions to a differential equation are functions, not numbers. Second result, basic finding, in many cases you have an infinite number of solutions. And if you want to visualize this, could be that F1, F2, F3, all of these functions are potential solutions to your differential equation. And how can you find a unique solution? by fixing a starting or a terminal value. For example, if I say f of 0 should be 1, then obviously this is the unique solution. I'll repeat this in German and then I'll leave you to it. Differentialgleichungen sind nichts anderes als Gleichungen, in denen Ableitungen vorkommen. Differentialquotienten. Wenn Sie gewöhnliche Differentialgleichungen haben, haben Sie nur die erste Ableitung drin. Oder nein, die erste Ableitung natürlich im Sinne, dass Sie nur in einer Variablen differenzieren können, in einer Dimension. Bei partiellen Differentialgleichungen haben Sie mehrdimensionale Funktionen. Das haben wir hier, ist hier der Fall, wir haben partielle Ableitung. So. Oben sehen Sie ein ganz einfaches Beispiel für eine partielle, für eine gewöhnliche Differentialgleichung. Einfach f' von x ist f von x. Damit man die Notation nicht immer so mit rumschleppen muss, macht man es einfach kürzer, y' gleich y. Simples Beispiel für die wahrscheinlich einfachste Differentialgleichung. Und die erste Feststellung ist Differentialgleichung, obwohl der Name Gleichung ja irgendwie suggeriert, ich spreche da eine Zahl raus. Eine Differentialgleichung hat als Lösung Funktionen, die die Differentialgleichung erfüllen. Und in fast allen Fällen haben Sie immer als Lösungsmenge eine Menge mit unendlich vielen Funktionen. In dem Fall fallen uns sofort zwei ein, nämlich die konstante Funktion, die 0 ist, und die Exponentialverteilung. Abgeleitet ist 0, 0 und Exponentialfunktion ist abgeleitet auch Exponentialverteilung, ist also gleich der ursprünglichen Funktion. Und wenn Sie dann eine Lösung herausfinden wollen, die einzigartig ist, brauchen Sie also eine Anfangs- oder eine Endwertbedingung. Wenn Sie nämlich jetzt sagen, ich habe eine, machen wir es nochmal komplett, Sie haben die Differentialgleichung y' gleich y, jetzt ist unserer geschrieben, Ableitung von y ist gleich y und y von 0 ist 1, dann wissen Sie, das ist eindeutig die Exponentialfunktion. Und das ist eigentlich die Funktionsweise bei allen Differentialgleichungen. Nur, Sie sehen schon, mit Raten kommen wir nicht weiter. Das ist der Teil, wo uns die Mathematiker dann mit ihren Lösungsverfahren für Differentialgleichungen helfen. Das will auch niemand mehr auf dem Papier rechnen unbedingt. Aber Sie haben eine Differentialgleichung und Sie brauchen eine Anfangs- oder eine Endwertbedingung. Und damit kann es dann im Idealfall sein, dass Sie eine solche Differentialgleichung eindeutig lösen können. This here is a stochastic partial differential equation. And as before and as here, we are interested in a solution to this Black-Scholes partial differential equation. The differential equation, I'll give you this in advance. This is actually here, this is the solution to the partial differential equation. How do we know this? Actually, the model is identical to a model from mathematical physics, the so-called heat equation. The heat equation describes how heat wanders through a rod of steel if it's heated at one side, and the heat, the warmth, goes through the rod of steel. And we know this result from mathematical physics. Now, the last question for today, and then I'll say goodbye. Does anyone have an idea what we are using as the start or terminal value? Was benutzen wir als Anfangs- oder Endwertbedingung, damit wir diese Differentialgleichung eindeutig lösen können? Hoffentlich. Es geht um ein Derivat. Was nehmen Sie? Den Preis vom Underline, der ist immer noch stochastisch, den kennen Sie ja nicht. Dann nehmen Sie was anderes. Und was haben Sie noch? Was wissen Sie ganz definitiv, jetzt schon? Das können Sie heute schon ausdrücken. In Abhängigkeit natürlich von ST. Das Auszahlungsprofil der Option in Groß T. Es ist keine Anfangswertbedingung, es ist eine Endwertbedingung. Sie wissen, was die Option ganz am Ende in der Fälligkeit wert ist. You know what the option is worth at maturity, when it expires. That's the payout profile of the option. And only in this very last step do you need the information of what type of derivative this is. Up to this point here, the solution to the partial differential equation, it includes P, and that's just a generic option or derivative profile. That's the payout profile. And it's a terminal value condition you're including, and then you can solve for the unique solution of this partial differential equation, and as a result you get the Black-Scholes pricing formula, a function. We'll talk about this in more detail next week, but think about it over the next week and how very general this Black-Scholes model is. Do you have any questions? Okay, so let's stop here and I'll see you next week. Thank you.